Hi, Algebra 2. So I am going to be going over your saying no to world hunger problem. And we're going to practice another linear programming problem and sort of just reviewing those steps to linear programming that you learned about when you were introduced to this peacekeeping problem. So remember last class you learned about how to approach a problem where we were trying to get as many Hummer units and as many helicopters overseas as possible. However, it had some constraints because we can only fit so much on a boat and area-wise and weight-wise. So this is the problem you were meant to complete after you watched that video of me going over the peacekeeping problem. And I did a lot of this for you. I wanted you to kind of fill in the pieces. So in this scenario, we are designing t-shirts, for this fundraiser. And I've got two types of t-shirts. I've got a child's face t-shirt, right? So a hungry child, get people's attention and donate, and then a custom design t-shirt. So the big thing here is you need to decide what is holding you back from your goal and what is helping you get there. So we have these things called constraints, which are going to hold us back from being able to, fundraise as much money as possible. So, more money than we could even afford, basically. So the first constraint, if you notice, is that we can have no more than 100 shirts. Okay, so before, we're going to read through this problem. You're going to read through these problems once, you're close reading here, and then you're going to read through again and underline, pick out all your important information. And then your next step will be to define or identify the variables, right? Because we're going to have two variables here that we're trying to solve for. We're trying to figure out how to maximize. So I have no more than 100 shirts. And another constraint is that I cannot spend more than $560. So it costs $5 to make a child's face shirt and $7 to make a custom tie-dye shirt. So I have to pay $5 for every child's face shirt I produce and $7 for every custom tie-dye shirt I produce. And I only have $560 to go towards this production. Now, in the next sentence, it says the profit for making and selling a t-shirt with a child face design is $3.50, and the profit for a custom design shirt is $5. So that is not a constraint. That's actually helping us towards our goal, and that's going to be part of our objective function. So the $3.50 per shirt and the $5 per shirt, that's going to help me in the end. That's helping me maximize my profit. So that's not actually going to be one of my inequalities because that's not holding me back from anything. It's helping me get to my goal. So I want to know the maximum profit from the fundraiser. So what I don't know here is I don't know how many child face shirts to produce and how many custom design shirts to produce. So I'm going to let X be the number of child face t-shirts and Y be the number of custom design t-shirts. So now I'm going to write my constraints. Well, these two are given, right? Because it doesn't make sense to have a negative number of child face of t-shirts, basically. That's not real life, okay? So we know that X must be greater than 0. We know that it can be equal to 0 because I can have 0 t-shirts. And the same thing goes for Y. So now my first constraint was that I can have no more than 100 shirts. So the total number of shirts, X plus Y, so child face shirts plus custom design shirts, needs to be less than or equal to 100. I can no more than 100 means I can have 100, but I can't exceed it. Less than or equal to. And then the other constraint is that I have a budget. So I cannot spend more than $560. And for every child face shirt I produce, I am paying $5 to do it. So if I produce 1, costs me $5. 2 costs me $10. 3, $15. Okay. And same thing goes for each of the custom shirts, $7 each. So here are my 4 constraints. Okay. This is what I wanted you to do. I wanted you to explain why those constraints do exactly what I just did there. And so now we're going to go, and our next step is going to be to graph these. So I'm going to jump right over to Desmos, and this is what you should do too. And you're going to enter these right into Desmos. So x is greater than or equal to 0. Y is greater than or equal to 0. 5x plus 7y is less than or equal to 560. And x plus y is less than or equal to 100. All right, so I have just a full shaded region here. That just means, look at these numbers, 560, 100. I'm in the 30s. I need to zoom out. There we go. Okay, so here's my graph. So the most important parts of this graph that I tried to talk to you about in the peacekeeping problem are the corner points. So we have developed a feasible region here. So this region is the quadruple shaded region, okay? And so it's this guy here bounded by the x and y axis. And I have 4 corner points. Why do I have 4 corner points? Well, I have 4 inequalities. So I'm going to have 4 corner points. So I've got 0, 0, 0, 80, 70, 30, and 100, 0. So those are my special corner points. And I'm now going to use those to help me minimize or maximize my, my objective function. So the question is, what is my objective function? Well, remember how much you're charging for each t-shirt? So we had $3.50 for each child face, $5 for each custom tie-dye. This right here is going to be my objective function. This is going to tell me what my profit is. So what I'm going to do is I'm going to take these 4 corner points and I'm going to evaluate them in this objective function. So easy one, if I sell no t-shirts, I make no money. Okay, so this next one, I sell 0 child face shirts and 80 custom shirts. Well, that goes away. $5 times 80 is just going to be $400 in profit. All right, and then I can do it, you know, this one. What if I only sell child face shirts and no custom design shirts? Now I've got $350. And lastly, what if I sell, you know, a healthy mix of both? 70 child face and 30 custom, and that ends up being $395. So let's just talk about these answers real quick. You should be able to see what the obvious answer is there, right? Which one's going to maximize our profit? It's that $400, in which case I am only selling 80 custom shirts. All right, so that is going to maximize my profit. Technically, that is the right answer. However, from a business standpoint, take a look at these other values. This one's not far off, okay? Yes, we'd be sacrificing $5. However, you know, we'd be getting a healthy mix of both types of shirts out there. So yes, this is the right answer, but you know, when it comes to real life, we're not always taking the right answer. We need to really take into consideration the right business move. So, you know, that's going to differ from everybody's different opinions. I would probably want to get, you know, a mix of both shirts out there, but somebody else might want to they just care about maximizing their profit. So something to consider there. So the next problem I'm going to show you is called Mira's Jobs, and I would like you to pause the video and read this problem now. So as you went through this problem, you notice that we've got Mira just trying to make, you know, as much money as possible, have some spending cash. So what I would have left you to do is go through and underline, pick out the most important information. In fact, why don't you pause the video again and go ahead and do that if you haven't already. Okay, so your important information should have been she can work at most 24 hours. We have an hour and a half preparation time for painting and a half an hour preparation time for mowing. Okay. See, she is not paid for preparation time, so she doesn't count this time in her work. Okay, so the 24 hours is just her work time, and she wants her total preparation time to be 18 hours per week. If Mira makes $12 an hour painting and $9 an hour mowing lawn, what's the best combination of hours of painting and mowing to make the most money? So I'm going to highlight that in orange because hopefully you recognize that's going to be part of my objective function. So after we've read and identified the important information, next we're going to define our variables. So I'm trying to figure out the best combination of hours painting and hours mowing. Okay, so now let's write our constraints, right? So we have constraints, or you can think of them as restrictions, and then we're going to have our objective function. So first of all, always consider, can the number of hours painting and the number of hours of mowing be negative? Absolutely not. So my first two inequalities are going to be restricting these values to positive numbers. All right, next, she can only work a total of 24 hours per week. So the number of hours painting and the number of hours of mowing cannot exceed 24. So that sum, that total needs to be less than or equal to 24. She's got to have a life as well. She's a high school student, so she's got to do her homework and go to school. All right, and then finally, we've got this idea of preparation time, right? You know, you're painting a room, we got to get drop cloth, we got to take the trim. There's a lot of preparation that goes into it. I would argue you probably don't need a half an hour preparation for mowing lawns, but maybe she's got to go get the gas, maintenance, you know, put some maintenance on her mower. Who knows? So she needs an hour and a half of preparation time for every hour she mows, and she needs a half an hour preparation time for every hour she mows. I think I said mow, I meant paint. Yeah. So an hour and a half for every hour she paints, and half an hour for every hour she mows. And this cannot exceed 18 hours. And the reason I use the less than or equal to is because it can be 18 hours, but at most 18 hours. All right, so those are our constraints. Now, as far as our objective goes, what numbers are going to help us maximize our profit right here, how much we're going to make? So I'm going to make $12 an hour painting, and I'm going to make $9 an hour mowing. And the total amount of money I make is going to be the sum of those two values. So we're going to jump right to Desmos because our next step is to graph this. And I'm going to go ahead right in. X greater than or equal to 0. Y is greater than or equal to 0. X plus Y is less than or equal to 24. And 1.5x plus 0.5y is less than or equal to 18. All right, so I'm a little zoomed out from before. So here is our graph. Let's check out those corner points. Okay, so I'm going to make note of those on my paper. So I've got 0, 0, 0, 24, 6, 18, and 12, 0. Okay, so just to reiterate, all of the values, all of the coordinate points within this region are going to work for this problem. She will be able to paint and mow the number of hours on every coordinate point in this quadruple shaded region, okay? However, they're not going to maximize her profit. These corner points are going to be the ones that could potentially maximize profit. So remember, each of these corner points are just 6 hours painting, 18 hours mowing. 0 hours painting, 24 hours mowing. So let's take those points and we're just going to evaluate them right into our objective function. So 12 times 0 plus 9 times 0. If we work no hours, we're getting $0. Okay, next one, all I'm doing here is I'm substituting the value of x and y for x and y in my objective function. So that's $216. 12 times 6 plus 9 times 18. $234. And lastly, 12 times 12 plus 9 times 0 is $144. So there you can see, here is the best combination of hours to maximize her profit. So Mira's looking at 6 hours of painting and 18 hours of mowing per week. And she will make $234. That's the most she can do, given, the things that are holding her back from working more.